Welcome to Group SML presentation. Today we want to present our assignment 2, which is image classification with supervised machine learning. My name is Eddie Pui. I'm the group leader.
My name is Samuel Chang. I'm the group member.
So let's move on to the table of contents. So first, we will start with the instruction to run code. But before we start with the instruction to run code, we will explain how we build our model, which are ResNet, in charge by me, and MobileNet, in charge by Samuel. And after that, following will be proceeded. So let's start with my ResNet models. Okay, so first, we will import libraries that we needed to be used. After that, we will import our data set, which is from Kaggers, Paley-Dotter competitions. After that, we will define our image rows and columns, which is 256, and then the batch size, and then the number of class, which is 10. Unicode, so means that there will be 10s. After that, we will use data augmentation, which will just rotate all the things one by one, and then improve our accuracy of the model and also prevent overfitting of our models. After that, we will train our images, import our image, import our validation, which will be just split into two lah. Then we will define our models. My model will be not using free-time models, so it means that we will just need to build a new models. So first we need to define our convolution models. After that, we need to build our models by dividing this. This will be explained in the slide later on. Then we will use our training setup, which will be import step 100, and then we will just keep training 100 times. If only it will just keep improving. This also will be explained later on in the slide. Then that's it. Let's move on to SAML models.
Okay. Now I will be talking about my MobileNet model. So in the first part, we imported all the necessary libraries and we mounted the Google Drive. Next, in the content in training files and test file is extracted to make sure that the system can read it. And we have set the epoch to 100, just like Eddie's, and the batch size to 32. The default image size for MobileNet is 224 x 224. And in the next part, here we are using the pre-trained convolutional layers, which are loaded using the ImageNet weights. And this part is basically used to just define the model of MobileNet. Next, we implemented the image data generator and the training data generator. And in the image data generator here, we can see that there's a line code validation split, which is used to split the training set into two, one for training purposes and one for validation purposes. And after that, we have set a model checkpoint. This model checkpoint is used to let the system save the best model throughout the training section. And in the next part, we can see here, after the training is done, we will have a section with the accuracy and loss data. And after that, the best model will be saved in this line, and it will be loaded, and it will be saved again in a .h file extension in the Google Drive. And that's it for my MobileNet model. Now I would like to talk about our Hugging Face app, where we implemented both ResNet and MobileNet into it. So here we can see that we have uploaded the both of the model, and we have created an file called app.python file. Inside this Python file, we can see that we loaded the model first and defined the classes. Next, in the image preprocessing section, we have resized the input images based on the model choice, whether it's ResNet with 256 x 256 or MobileNet with 224 x 224. And we will let the user to actually choose which model do they want when they are using the app, used to predict the classes of the images. And this is an example of how to use our app. So firstly, the user can upload the images, and after that, they are free to choose whether to use MobileNet or ResNet. So in this case, I will be showing ResNet and click submit, and then we will see that the result will be outputted here to show that what is the disease of these images is bacterial leaf blight, which is correct because I extracted this example of this photo from the bacterial leaf blight file. And now we will move back on to the slides. Next, we implemented the image data generator and the training data generator. And in the image data generator here, we can see that there's a line code validation split, which is used to split the training set into two, one for training purposes and one for validation purposes. And after that, we have set a model checkpoint. This model checkpoint is used to let the system save the best model throughout the training section. And in the next part, we can see here okay, moving on, we will talk about the data preparation and preprocessing. Firstly, we can see that the dataset used is the PADI-Doctor. And the reason behind this is because of its quality and relevance to agriculture applications. We have narrowed the dataset to 200 images per class for the training and 100 for testing. These 200 and 100 images are both extracted from the original dataset size with 1000 images per classes. And in the pre-processing steps, the images were resized and normalized to match the model input requirements. And after that, the dataset was split from the original 1000 images, and we have made sure of an unbiased testing. In the potential application here, this model approach or this app approach is particularly suited for building tools like real-time diagnosis, apps for farmers. And next, Eddie will talk about the training section of ResNet.
Thank you, Samuel. Let's talk about ResNet. So why we choose ResNet? ResNet have a high performance across tasks and also faster conversions. Next. So how ResNet works? So ResNet works like this. First, you add residual connection to the network, which help to maintain information flow throughout the network and prevent the gradients from vanishing. What is residual connection? So residual connection is a shortcut that allows the information to bypass one or more layers in the network and reach the output directly. So there will be an example of the architectures for the ResNet. So you can see he will just bypass a layer, web layer, and then just go into the output directly. So this will allow the network to learn residual functions and make small adapt to the parameters. It's easier to learn the residual functions which map the input to the desired outputs. Next, let's move on to training procedure. First, we will just as my model is not a pretrained model, so it will just build on new ResNet models. First, it will just use input layers. First, it will just build the input layer. So input layer will be accepting the image, which will be in 256 height and 256 rows and columns, 256 and 256, and there will be 3 colors that will be accepted. After that, it will use convolutional layers, which will be 2. These 2 will be extract features following layers and also reduce the size. After that, it will after that I will just build after that we build a residual blocks. Residual block is used to refine the features with skip connections. Then we will build the global average polling layers, which will be used to reduce features to a single vector. Then the fully connected layers will be used to make prediction, and then output layer will be used to produce the class probabilities. So the training setup will be this. Epoch will be set 100, and then it will adjust the learning rate dynamically during the training. And this throughout this training, it will just monitor the loss. So if there will be no improvement in epoch, the training will be stopped, and then he will just save the models, the best models. That's it for me. Let's move on to Samuel's models.
Okay.
Let's move on to training procedure. First, we will just as my model is not a pretrained model, so it will just build on new ResNet models. First, it will just use input layers. First, it will just build the input layer. So input layer will be accepting the image, which will be in 256 height and 256 rows and columns, 256 and 256, and there will be 3.
Now I'll be talking about MobileNet. So MobileNet is a lightweight and efficient convolutional neural network, which stands for CNN, designed for mobile and embedded system. Unlike traditional CNN, MobileNet uses a strategy known as depth-wise separable convolution, which stands for DSV, to reduce the computational cost while maintaining performance. This makes it ideal for mobile devices which have limited processing power and memory resources. So how MobileNet works? So at first, as you can see in the images, the input is a 224 times 224 times 3 image, where 3 represents the RGB color channels. So in the first convolutional layer, a standard 3 times 3 convolution is applied to increase the depth to 32 filters. And next, the depth-wise separable convolution, which is the DSV, is a core component of MobileNet, which is used extensively throughout the whole architecture of MobileNet. Each DSC block performs a special filtering, which is depth-wise convolution, followed by a feature combination, which is the point-wise convolution. It replaces the traditional convolution to improve efficiency. And the layers are organized into stages, where the first stage consists of 2 DSCOM layers with 32 filters, and the output size is 112 times 112 times 32, while the second layer has increased to 64 filters with the output size of 56 times 56 times 64. And it will keep going on until the last layer, which is the softmax layer, keeping the size of the output to 1 times 1 times 1024. So the feature extraction of this MobileNet captures the features of the PADI disease images using convolutional layers, and it will focus on spatial and channel information. And for the classification parts, MobileNet will use the fully connected layer to classify the images into one of the 10 classes. And now I would like to talk about the training procedure of the MobileNet. So in my case, I'm using a pre-trained MobileNet model as the base model. And this means that the weight of MobileNet trained on a large dataset like ImageNet were used to initialize the model. Pre-trained model helps to leverage features learned from large datasets, reducing the need for extensive training and improving performance on smaller datasets. To adapt MobileNet for the specific classification task of this, additional layers were added. So firstly, global average pooling, which stands for GAP layer. This replaces the fully connected layers of the original MobileNet. It averages the spatial dimensions of the features map, reducing the features map size to a single vector. This reduces the overfitting and the number of trainable parameters, which helps to increase the efficiency. And for the fully connected dense layer, a dense layer was added with a softmax activation function. Softmax ensures the output is a probability distribution across the 10 classes, making it suitable for multi-class classification like this task. And in the training setup, the optimizer called Adam is widely used because it is very efficient for weights updates. It adjusts the learning rates for each parameter dynamically, combining the benefits of RMS-probe and stochastic gradient descent, which stands for SGD. Since it is a multi-class classification problem, categorical cross-entropy measures the distance between the predicted probability distribution and the true levels. Accuracy is used as a primary evaluation metric to measure how well the model predicts the correct class. And for data augmentation artificially increases the size and variability of the training datasets. This is crucial for preventing overfitting, especially when working with small datasets like this task. In the next slide, we will talk about the selected parameters. A learning rate of 0.001 is a commonly used default for stable convergence. It is neither too small, which would cause the training to be very slow, nor too large, which might cause the model to miss the optimal solutions. Next, the batch size used in this task is 32, which strikes a balance between memory usage, as smaller batches use less memory, making it manageable on most GPUs. The training size, we are training on 100 epochs, which provides enough iterations for the models to learn patterns from the data, ensuring it converges without underfitting or overfitting. And next, the input size is 224 times 224 pixel, which is the standard input image size for MobileNet. Next, let's talk about the model evaluation procedure. So to train and evaluate the model effectively, the data sets was divided into 3 parts, which is the training set, which is used to train the model by adjusting its weights based on the input data and levels. The validation set, which was split from the training set files, is used to monitor the model during training and tune hyperparameters like learning rates, batch size, and etc. In the test set, is used to assess the model's final performance after training is complete to see if the model actually works well. For the evaluation method, we are using confusion matrix and ROC AOC curve. So confusion matrix is a tabular presentation showing the counts of true positive, true negatives, false positive, and false negative. While ROC AOC, which stands for receiver operating characteristics area under the curve, is a graph that plots the true positive rates against the false positive rates at various thresholds. While AOC is the area under the curve of the graph, which represents the model's ability to distinguish between classes. So how our results measured? We are using the evaluation method mentioned earlier, which is the confusion matrix and ROC AOC curve. The confusion matrix will illustrate the correct versus incorrect prediction for each class, providing a very detailed view of the model's performance. It also helps identify which classes are being confused, offering insights into potential areas for improvement, while the ROC AOC curve plots the true positive rates against the false positive rates to evaluate the classifier's performance. It measures the model's ability to distinguish between classes at various decision thresholds. Now, allow me to let Eddie to talk about the discussion part where the illustration of confusion matrix and ROC curve will be shown also.
Thank you, Samuel, for his explanation. So let's talk about the ResNet confusion matrix result. So overall, this model has a correct prediction as the diagonal value are very high, as we can see. The best performing class will be bacteria leaf streak, which has the 94 correct prediction. And the worst performing class will be the HESPA and bacteria leaf blight, which have 45 correct predictions. Let's move on to the MobileNet confusion matrix. So compared with the ResNet one, we can see that MobileNet will be having a better result. As we can see, the diagonal value will be very high, and then there will be a lot of dark color, which indicate a lot of which indicate a lot prediction will be numbers. A lot of the prediction values are very high. So the best performing class for in this MobileNet will be Donny Mildew, and the worst performing class will be Bronzewort, which have 67 correct answers. Let's move on to ROC AOC curves of ResNet. As we can see, the ResNet curve, the ResNet ROC curve overall performance is good. As we can see, all the values are high, and then it makes a good shape of it. So the best performing class we can, as we can see, will be the bacteria leaf streaks, which have the value of area under the curve 0.99, which will be a very high values, as the maximum value will be 1. And then the worst performing class will be Congruo, which have 0.85. However, it still is a good classes as it is higher than 0.5. Let's move on to mobile nets. So mobile net performance is good as all the classes is higher than 0.5. Besides that, it also makes a good curve. The best performing class will be Bactrian Pinnacle Blights, which have 1.0, which means that he predict all the things right. And then the worst performing class will be Bronze Spots, which having 0.87, as you can see. But however, it's still a good classes, but it's just the worst performing class among all the classes. Let's move on to the next ones. So let's talk about the limitation of the approach. So first, class imbalance. So the class, if all the classes did not have the same amount of sample size, it will affect the model ability to learn effectively. For example, the model will be biased to the classes that have more example as models. The models see more example of the classes that have a lot of more amount than others. Besides that, similar pattern of the plants will also make the model perform worstly, as the similar pattern will cause the model to confuse and then will predict wrongly. Bad quality of input image will also lead the model to be fail learning meaningful relationship. Next. So under which condition the approach will fail? Similar patterns of the plants. So as just now we talked about the similar pattern of the plant will just confuse the models to predict wrongly, as there will be similar patterns among all the classes. Besides that, small data size. So small data size will cause the model to fail to learn the patterns, as there will be little data to be learned, and they will be overfitting all the things. And if the data consists of a lot of noise, it will confuse the model to predict wrongly, since it will just focus on the wrong relationships. Next. So which conditions where the approach will be work better? Distinct classes features. So as just now we said that when the conditions when the classes that share a lot of similar patterns will let the approach fails. So if the classes have different visual features, it will let the models to work better, as there will be really different things that can be identified by the models to be predict the classes are. So big data science also will let the model work better, as there will be a lot of parameters to be learned, and then reduce the risk of overfitting. High quality image also will cause the model to be perform better with a high resolutions, and then noise-free image, so that he will just focus on the good important things to be learned. Next. Okay. So our classifier can be improved by using bigger data set, also fine-tune pre-trained models. As we can see just now, Sam is using pre-trained models, but I'm using models that does not be pre-trained before. So it means that I just rebuild a models. So as you can see the results, pre-trained model, fine-tune a pre-trained model will be better, as the result that come out is better than a model that be built newly. Besides that, we also can enhance our data augmentations, and then which will be improve our accuracy and also reduce overfittings. Next. So let's talk about the key areas that we can be optimized. First, data collection and preparation phase. We can use a bigger data sets so that the model can be trained more. Besides that, we also can design a better data augmentations, which will improve our accuracy and also fine-tune our models. It's not for the sorry, is reduce our overfittings of our models. Besides, and when at the model training phase, we can use pre-trained models and also fine-tune the models better, as we can see, the mobile net which use the pre-trained models is having a better results compared with my ResNet that does not use a pre-trained models. Next. So there will be a difference on choosing more or less classes. First, if we choose more classes, the model need to learn, it will increase complexity, as the model need to learn more classes and then define the difference between the classes. Besides that, there will be a high risk of class imbalance, as there might be not enough sample size to fit to have the same amount of classes to have the same amount of data among all the classes. Besides, other than that, it also consists of longer training time as models need to use more time to define and to differentiate all the classes. So if we choose fewer classes, it will be simpler complexity and also lower risk of class imbalance as we can prepare less classes with more data set. Besides that, the most important will be faster training times as the model does not really need a long time to train our models to identify the classes. Next. So let's talk about the key areas that we can be optimized. First, data collection and preparation phase. We can use a bigger data sets so that the model can be trained more. Besides that, we also can design a better data augmentations, which will improve our accuracy and also fine-tune our models. It's not sorry, is reduce our overfittings of our models. Besides, and when at the model training phase, we can use a pre-trained model. So let's talk about the data preprocessing. It was really important to do data preprocessing as it will let our image be uniform. For example, we can just resize all the image to the size that we want. For example, for me, I'm using 256, and then Samuel will be using 224 and 224 for his mobile nets. In the data preprocessing, we also can enhance our image feature. For example, we can highlight the important parts inside our image so that the model can be easily identify the difference between all the image and all the classes. Besides that, we also by using data preprocessing, we also can improve our image classification accuracy, as we just need to enhance our image in futures by highlighting all the things, all the important parts, and the model will be learning easily, and also the accuracy will be improved. That's all for me. Let's move on to semester 1.
Okay, thank you, Eddie. So in conclusion, for the summary of findings, mobile weight is lightweight and has a faster convergence, which is suitable for resource-constrained environments such as mobile devices and embedded system, while ResNet is better for complex datasets but requires more computational power. For the evaluation results, MobileNet shows a higher accuracy and AUC, which is efficient for deployment on mobile or edge devices, while ResNet outputs a competitive accuracy and robustness, but it has a better feature for representation for challenging classes. In my opinion, for best approaches, both models are actually good, but MobileNet will be more useful for speed and efficiency in low resource scenarios, such as to be used in mobile devices, while ResNet will be good to be used for maximum accuracy in high stack application with larger datasets. And that's it for our presentation. Thank you.